Can everybody hear me?
Yes.
All right.
Yes.
Okay, perfect. Okay, so let me just remind you that on under modules, I have incorporated. So I'm trying to give you as much explanation as I can. But a couple of things. So I have incorporated a number of Smith charts that you may select to use for this week and next week. And I have given you some guidance of which Smith chart has the best resolution. Because if you go through all of those, you will see that they change in terms of resolution. And so you can select, you can download, do your work on that and then upload again and make usually for homework or for any other activities. Okay, this is dead. Or it's not dead. The battery is gonna go down very quickly. So I'm gonna try to speak loudly. In any case, so when you go to this in the files under, it is also in the files, right? So this one is not working. So can you hear me right now? No? Okay, well, you know, I don't have batteries with me. Let me call them. Oh. Let me call them to bring some batteries. Hello, could you please bring some batteries for the microphone? Thank you. All right, well, let's try to do as much as we can with what we have. All right, so when you go to modules and also in files, I'm trying to use the same kind of arrangement that we have in modules, also in the files. But number one, we are going to introduce the Smith chart today, and I gave you different options, and you're going to see what we are talking about. This is not okay. All right. In any case, the second is module 13, where we are today, and we are going to do a top hat exercising class. And as you do that, I'm going to bring a Smith chart. We are going to try to read the Smith chart today, so you know how to, you know, make yourself comfortable. And then there are some exercises for you to do. We're going to try while we are reading it to do some exercises. And then I also have what I'm trying to do this week with transmission lines is also create a couple of documents for you that you would need to refer to, where everything is going to be written there. And there are two documents that I suggest you also follow, all right? Follow very carefully and use them. And those will be the review of transmission line equations. Okay, this one. Is going to be the review on transmission line equations, and then also a summary of important transmission line equations. Thank you. Thank you. That you need to use. So make sure that you will see those documents. I will use them from one module to another, because as we add equations, we are going to put them on the same documents, and then you have them available when you do your work, homework, anything else you study, and then the finals. All right, so let me start with the top hat, as I'm gonna bring the one of the charts to use, the Smith charts. So we're going to this. And these are all for review, just to bring to you some of the concepts that we are using. So I'm going to unassign this. That was what you had to do today. And then assign it as a review. And then we're going to now unassign that too. Assign it as a review. And then we are going to week 14 and then look at the matching circuits. And it says the following: on the basis of what the equations we've seen and what we've discussed. So you have a 50 ohm transmission line that is terminated in this load. The load has a real part, 50 ohms, and imaginary part, J 50 ohms. Which of the following statements is correct? The line is already matched. We can match this line with a quarter wavelength transformer. You remember that from last week. We can match this line with a series open circuit stub placed at half a wavelength from the load. And so open circuit, you need to remember what brings the input impedance. An open circuit is equivalent to an impedance, all right, which is reactive. You remember that from open circuit? And we can match the line with a series quarter wave short circuit stub placed anywhere on the transmission line. So I would say, because you may find it a little challenging the way it's stated, what I will do is that how about if I edit it before you do it? Because it might take you some time, all right? So I will take it off. I'm not gonna give you that, don't worry. I'm gonna edit it and give you something else. So I will remove those things. Don't worry about that. So let me, for a moment, I will stop the broadcasting and also I will stop this. So I'm gonna make it a little simpler, right? How about that? That's all that I will do. But it's about matching. I will just make it a little simpler. So that. All right, the simplest thing is this one. I will make it very simple. How about that? Okay, and this one. Okay, so let me save it. Now, ready. All right. And I will also share screen. All right, so now you're gonna see, but don't wait until I'm telling you to start, because otherwise it's gonna show what people are doing. So don't start until I read it, so you see what it is, and then I will turn it off, and then you can continue. So that takes some time, all right? All right, so here, all right, now it says the following. Consider a 100 ohm transmission line 100 ohms transmission line, Z naught is 100 ohms, terminated at a load which is 50 ohms. Which of the following statements is correct? The line is already matched. We can match this line with a quarter wavelength transformer, and we can match this line with the other two things that I gave you. All right. So I will assign it for homework, and then I will get out of this. All right. So you can do your work, and then I will bring with what we've learned last week, you can work on this. And I will bring whatever I need to this one here, but not that one, while you're working on it. Somebody, you need to, there is somebody who has the microphone on and we can hear scratches and stuff. So if you can mute yourselves. Are you ready? Yes? No? You're supposed to do this very fast. Because I said something last week that is supposed to make it very fast and easy. What did I say? What do we do when we have a resistive load only? How do we match it? With? Yeah. Do you remember? No? With a something that starts with a T, quarter what? Okay. That's how you're supposed to remember it quickly. That's why we remember. You remember what I told you, that we've learned a few tricks. We don't start from scratch. We learn a few things that other people have done and worked. So that, write it down, and then I will turn it off so we can move. So let me, in fact, go there. Cancel. Go to that. Go here. There. Yes. In fact, I'll show it to you and then I will turn it off. So the correct answer is this. So unassign it. Yes, it is a quarter wavelength transformer. Whenever you have a resistive load, you're not going to do anything else, because anything else is going to be a waste of your time. You're going to do every time you have a resistive load only, you're going to do a quarter wavelength transformer. You're not going to think of anything else. All right. You're going to start thinking of other things when your load is complex. And now, having said that, we are going to go to the Smith chart. Now, we are going to start with the Smith chart and then get familiar with it. But in the problems I'm giving you, I will ask you to do both. All right, we'll do the analysis and then we'll do the Smith chart starting on Wednesday. You will see it also in the new homework that I have given you. Smith chart and then equations to check it out, to make sure you get familiar with both. Eventually, people are using only in the Smith chart. If you go and take 453, then you're going to see we're going to use the Smith chart exclusively because the equations get too messy. And then you cannot even do design with equations. It's only for analysis. It's just to tell you that your result on the Smith chart is correct. All right, if you want to check it out. Okay, so I will assign it as a review. And now we're going to the Smith chart. Okay, here, that's how it looks. Most of the Smith charts we're going to use have this lower meter. And I will explain to you what that means. Between now and Wednesday, the only thing that I would like you to do is to become familiar with that, to look at it and then realize, at least remember what I told you about how to read it. All right, first of all, we'll start with the lower meter to see what it says here. All right, first of all, always well, let me also remind you of the following, or at least introduce the center of the Smith chart. Very important point. Every time on a Smith chart, whenever you are at the center, and I will explain what that means, but whenever we are at the center, it means that we have achieved a perfect match. So the goal in the Smith chart, wherever you start with, we'll see how we're going to identify your load. Your goal is to eventually go there, but you cannot just go straight. We'll talk about this. But before we get to all of this, let's start about and think about the what we are reading here. I will erase. I like this because it's clean, and you can read the other ones. You will see that they are kind of fuzzy. But the only thing that I would do here is to erase this one. No, sorry. This one. All right, I will erase this. And I will put here that we are using the upper bar, this one, all right. We use this to measure the VSWR. Okay. Measure VSWR. VSWR here, VSWR. And what you're going to see, it starts at 1. As we say, it cannot go below 1, all right? And then it goes to infinity. So from 1 to infinity. And then nothing else there. And then we are going to another mark. See, everybody's using different, I'm erasing those because they're not using our own nomenclature. So here, reflection coefficient, comma. So that we are going to measure the reflection coefficient. okay, gamma. And it's going to be a different square. This one. Not collaborating. All right. So it starts at 0. You see 0 here. 0. And then it goes to 1. Because the reflection coefficient cannot go anywhere else. It's between 0 and 1. Between 0 and 1. All right. And while the VSWR, when the reflection is 0, becomes 1. And when the reflection coefficient is 1, becomes infinity. Do you remember those things that we saw them last time? So here you see how they have arranged that on the Smith chart, but we're not going to see anything else. These are the two measures, all right? They are measures and they are logarithmic. They're not, so they use them though because they can, as you will see later, use them together with the Smith chart. The reason I want to show you that because there are a lot of Smith charts without the lower bar, and the lower bar is useful to have it. So whenever you use a Smith chart, try to also find the one with the lower bar. All right, so now let's leave this for a moment. We'll come back to it next time and start looking at the Smith chart because there are a lot of things here. So first of all, I will, let me use also, yeah, this is thick enough. I'm gonna go around the outer ring. The outer ring is this one. All right, goes all the way around. Now you're not gonna do it all the time. I'm just trying to do this right now to help you. The outer ring also has an arrow here. In fact, it has a couple of things. Let me erase part of it so we can read them, all right? It says here, if you look at that, it's not in English, but it will say, that's why the other things were different. But it will say, if you look at the other Smith charts, it will say towards the generator, all right? So here, it says towards generator. So obviously it's a movement, all right? It shows that if I have a transmission line here, and then duplicate that. And if the line has a load at the end, all right, here, and the load is Isabel equal to Isabel plus, and I use different colors because we are going to use different of those lines, Xabel. First of all, to use the Smith chart, what you do is that you have to normalize all of this with respect to the characteristic impedance of the line. So practically, Isabel is normalized, is this one divided by Z sub naught, which means that R sub L normalized is this, and X sub L normalized is this one. All right? So everything, that's why you're not gonna see ohms, you're gonna see just numbers. So now, if I start moving, these are my, you remember the two ports. This is the port where I place my generator. A prime. And that's where I place the generator here. This base. This is the output port, B prime. All right. And let's assume now that I want to move from the load towards the generator. That means that the motion I can do on this Smith chart when I move from the load towards the generator, all right, so I move like this. It can go only around circles like that, all right, and then you can read it. So it's all in wavelengths, in lambda. So if I were to move from this point to this point, that means that I have moved from the load to the generator, since here it starts at 0, by 0.06 lambda is what you read. And if I keep moving, here is 0.12 lambda. And if I keep moving, here is 0.25 lambda. And if I go all around the circle, I come back to where I was, and that's half a wavelength. All right, so practically what that tells you is that every half a wavelength, all of the values of the impedances repeat themselves. So remind me, and I will remind you of that concept when we plot the impedances. That means, therefore, that if I want to move on the transmission line, the only motion I can do it in circles which are concentric, and their centers are at the center of the Smith chart. So if I find, for example, somewhere, and all of the values that you see here, the points, all the points here on this surface will correspond to impedances. All right. So let's assume, and I will show you that next to you how I'm going to get there. But let's assume that I find myself all of a sudden that I have a load and I'm here. So I'm at this point on the Smith chart, and I am right at the load. All right, and let's assume that this is Isabel normalized. We'll find out how we find ourselves there. But let's assume now for a moment that I'm here. This is our space. This is the whole space on transmission lines, all right? It's a space that every half a wavelength repeats itself. Therefore, on a transmission line, when you move from your load by half a wavelength, then you can only move on concentric circles. So now I'm gonna write this circle. Okay, so hopefully it's gonna collaborate. This one. Okay, this circle okay, with a little bit of an effort. This circle is called the constant Vswr circle, or the constant magnitude of reflection coefficient. But instead of saying all of this, the constant magnitude of reflection coefficient, I say the constant Vswr. Why do I say that? Tell me, if I am on a transmission line like this, and I move from B to A, at every point on this transmission line, how does the Vswr change? Let's start with the Vswr. Do you remember how do we calculate Vswr? 1 plus is a ratio. The Vswr on this line is what? 1 plus the magnitude of the reflection coefficient, 1 minus the magnitude of the reflection coefficient at whatever point of the line you are. What did we say about the magnitude of the reflection coefficient? What is the magnitude of the reflection coefficient on a transmission line? Does it change? How does it change? Either it changes or it does not change. And if it changes, how does it change? What do you think? Pardon me? It does not change. Do you remember when he said that the magnitude of the reflection coefficient is the same everywhere on the transmission line? Because it's only the phase that changes, only the phase of the reflection coefficient. The reflection coefficient has the same magnitude, which is the magnitude of the reflection coefficient at the load. And as you move along the line, if the line is just like this without anything added to it, then the only thing you do is to change its phase. All right. And we have found that at any point Z on the transmission line, the reflection coefficient is gamma sub L E minus J to beta D, where D is your distance from the load. Remember that? D is the distance. That's why it is important to have these formulas next to you. All right. So now, since this is true, and then if I have a given load, then my VSWR on the transmission line, does it change or remains the same everywhere? It stays the same. And that's why when I move on the transmission line, everywhere on the transmission line, the VSWR is a constant. And that's why I call this circle the constant VSWR circle. All right, if I say that, that means wherever I move here, I will move along the line. Now, how I move, whether I go clockwise or counterclockwise, it tells me which direction I'm going. All right, so if I start from the load and I go this way, then I'm moving from the load towards the generator. Here, it says that. It reminds you that this direction is towards the generator. All right? So I go from the load and I can go until I find my source, or however length is my line. Let's assume now that I gave you this Isabel, I gave you this point, and I want to move, and I also told you that the length of this line, that the length of the line, which we indicate by L, is 0.3 of lambda. Okay, then how am I going to find this? Then I draw this line here from the center of the chart. I draw this line. Okay, and then so we don't have too many lines. I do it like that. Okay. And then I read here in the outer circle, I will remove this now for a moment. So, but in this outer circle, I read it. And if I read carefully, all right, let me remove this for a moment and I will remove the rest. If I move carefully, if I read carefully, this is 0.06, 0.07, therefore this 0.08, and therefore this point here is 0.082. That's the point here. And then I want to move by 0.3 of a wavelength. So from this, I want to move this way by a 0.3 lambda. So I just add 0.082 lambda to 0.3. And I have therefore to find it's going to give 0.382 lambda. I have to find where that point is. So I go around the outer circle everywhere until, see all of these numbers that increase, all of these numbers increase. I pass the 0.25 point, and then I keep going. 0.3 down here. And then I have to go 0.382. So 0.3 down here, 0.38 is down here. 0.382 is exactly here. All right. So now I have to connect this point to that. Also make it, so I avoid, I don't want to have too many lines. And right here, is the point where I find the input impedance at my source. So if I move there from ZL all the way around, and usually the way I show the motion in on the Smith chart, oops. So, and it's like this. I do it because a lot of times which direction you go is important and when you stop. So a lot of times I will do this with these small arrows. So I know why I came to this point and where I came from. All right. So that is the input impedance at the source. And because the source is connected to a prime port, that point there is the input impedance at my source. See, I find it without solving the equations that have hyperbolic tangents. Okay. So now, let's see how we found that point, Isabel. And let me write it first and then I'll do the reverse. So let me assume that I give you here that Isabel normalized, so I divided already for you, is 0.52, not exactly, is 0.25. Okay, the real part, 0.25 plus J 0.5, like 7. Okay, let's assume that I gave you that. And you did not know how to find it. And how would I find these points, Isabel? I just show you now why this circle is important, but I did not tell you how we found this point. So now we are going to find that if I did not give you this point on the Smith chart by myself, but I gave you the value of the normalized impedance, how would you get the point on the Smith chart? All right, because the Smith chart gives you all possible points of impedances, everything from 0 to infinity, if you like. And real and reactive, it's a whole thing. It brings the whole space of numbers, complex numbers in here. This is the value of something. I mean, the person Smith, whatever his name was, and whoever this person is. I mean, the way it was a brilliant thought to think about that at the time when they had no computers. they mapped an infinite space of complex numbers, two-dimensional infinite space, into this. That was what he did in a brilliant way. So how do we find that? There are three types of circles on this, all right? And what I would like to do for a moment is to add here a page, add page, and then move this above. Can I move it or no? Yes. And then I will copy this, come here and paste it. But I will remove everything else. All right, so the only thing I want to do here before is to show you how to find every point, any impedance on the Smith chart. Any. All right, so now we'll start with the impedance that leads you to the problem we already solved. And I told you that the impedance is 0.25 plus j 0.57. So I'm telling you that in this circuit here, Z sub L is 50 times 0.25, a quarter of 50. How much is that? 12.5. 20.5 plus 50 times almost like 25. Could you tell me how much is plus? J is like 26. What is it? 28. Let's do this, right? And I will put 12. Yeah, okay, 12.5 is good. All right, so somebody tells you that this is all in ohms. Okay, so they give you this problem and say now, in this problem, find if your load is this, find Z input at A prime using the Smith chart. It's not South Carolina, it's the Smith chart. I don't know. Okay. First of all, what you do, so to solve the problem, you normalize the load. You find 12.5 plus J28 divided by 50, which in fact, now it was ohms, now becomes a number, it is 0.25 plus J 0.57. Okay. So now I have to find this complex number. On this Smith chart, which I brought here, you see, there are, obviously you can tell that there are some circles here. Right? There is a group of circles that go like that. So there is a group of circles, and I will show you one at least, that go like this. They have their centers on this horizontal axis. So their centers are on this axis here. That goes through the center of the Smith chart. And also I'm gonna do it like that. Okay, and then they are all tangential to this point. So this is one that goes through the center of the chart. You will see that we are going to use this circle quite a lot. And then that's the center. And then there is another one here. Okay, and then there is a bigger one here somewhere. There. Okay. So every one of these circles corresponds to a value on this axis. If you look at the horizontal axis very closely, you will see that there are numbers. Okay, let me move this a little bit. So the only thing in the old days is that you had to have very good eyesight. Otherwise, you could not see because everything was on paper. So in any case, you will see all of these numbers. They start at 0 here, and they go 0.1, 0.2, 0.3, 0.4, 5, like algorithmically, 0.6, 0.7, 0.8, 0.1, 0.9, 1 at the center. And then 1.2, 1.4, down to this point, which is 2.0. Down here, 3.0. And then so forth. They go here to 10, 20. And then at the point where all the circles are tangential to a line which is perpendicular to the horizontal, that corresponds to infinity. Now, infinity, what does it mean in terms of, in circuit terms? If you have an infinite impedance, what does it mean? Your circuit is open. So all of these points represent open circuits and impedance form. And all of the other points on the other time part of the axis. The other part of the axis here, you will see that its value is 0. So where does this correspond to? Short circuit. Short circuit here, open circuits there. See, from 0 to infinity, all of these values using logarithmic scales. So every of these circles corresponds, has one of these values, which means that all of the points on this circle, every point here is a load. Every point is an input impedance. It could be a load, it could be an input impedance somewhere in your line. So it has a real and an imaginary part. So all of the points which are on the perimetry of each circle have the same resistive value. All right, so all of the loads on this circle and the large one, all of the loads on this circle, they have a value which is 0.32. All right, normalized 0.32. So, is that right? Yeah, here. 0.32. You see 0.3, and that's another 0.32. All of the points on this circle have the resistive part. So I can write any point on this circle. If I use, for example, this color, that is a load of some sort, an input impedance of some sort, all right? It's an impedance, obviously. This here, let's call it input impedance, could be a load. It has a normalized real part, which is 0.32. And of course, it has an imaginary part, which we don't know yet. All right, but all of these points, all of the red points, have on this particular circle have the same point, real part normalized. Okay, now keep that in mind. I will erase this for a moment, because the point here we want to explain the circles, but eventually we want to find the impedance that they gave us, the 0.25. So practically, now that I know that all of these points have the same real part, I will move this circle to go to the 0.25 here. So I'm going to move this to go here. All right, so now what happens? All of these points of this circle have a real, normalized real part, which is 0.25. But now, from all of these points that have the same normalized real part, I want to find the one who also has a 0.57 as reactive normalized. All right. How are you going to do that? There are these other circles. You see these lines here that go like this? There are circles up on the northern hemisphere, and then in the southern. The difference between the northern part of the half upper part of the circle and the half lower part is in the sign. It says here, it says, those who speak Spanish, I think you will be able to find what it says, but it says component, reactive component, which is inductive. So all of the values here are positive, and all of the values here are negative. An inductive component here means your impedance is like JX plus positive, all right? So the way I gave you this impedance, it's a resistor. It's a resistor plus an inductor, the way I gave it to you. Do you agree with that? Because the reactive part is positive. So I'm looking up here to find the circle, which I'm gonna intersect with this red one, but which corresponds to 0.57. Okay, these circles also, let me draw one. That not. So do another one. Let's go through 0.5. No, okay, I have to do it by hand. Don't leave yet until I finish this. Okay. Not good drawing, but in any case, this circle here goes through, you see, it says 0.0 again, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, all the way. Here is 1, and then here is infinity. But you measure the resistive parts here and the reactive parts on this lower circle, just lower. So I go and find the circle that starts at 0.57, which is approximately here, because this is 0.55 and it should be this 0.57. And then I draw the circle until I find at what point it intersects with my circle of the real part. And I find that more or less, and there is a lot of flexibility, you know, to make some, to not draw very well, but here is the intersection point. So this one is my load for the transmission line, all right? Which is right there. So practically, the first step is to find the load, all right, to find it on the Smith chart from the transmission line. And then the next step is to move around that transmission line. The moment you find your load, this is how you move along the line until you come to the front part of it where it connects with the source. So this is an example. I will stop here, but what I would like you to do is take the Smith chart, any of the Smith charts that I put there without anything, they're clean, you can download it. And then do something similar. I want you, if you don't do it yourselves, if you don't try to find, give yourselves a few examples and try to find the loads, you're gonna always not be able to follow the problems we're gonna solve, because by the time I will start doing something else, you're gonna struggle to find a point on the Smith chart. So do some practice. It's not intellectually difficult. All right, it's a simple, there are few only, it looks complex, but if you play with that a bit, you're gonna be able then and feel comfortable yourselves find the points on the Smith chart, then we can do other examples with this. All right, so we are gonna continue with this on Wednesday. All right. And on Wednesday, I'll give you a problem. I'll give us a problem rather. All right, thank you.